three software products. Safe single break, something called safe range monitoring, and finally something called safe operation. Now, correctly used, these could also not only be used for a safety issue, but also to reduce a cell footprint or space, and perhaps even the cycle times. So let's have a little bit closer look into it. So normally, or the easiest way to handle a robot safety is to build a fence, and you will put this fence outside the total robot reach. And then we could have various access methods for operators. That could be a gate or a light curtain or anything like this. Now, if we instead imply our simplest solution here, which is called safe single break. Sorry. That is actually a solution which I've tried to depict here in this small picture here, where we have the robot mounted inside a closed cell. But instead we have a turntable here where the operator loads and unloads his goods. And what safe single break does is then actually to have a safe stop of this driven access for this. Okay, Laurie can't see everything I'm showing. Wonder if we have a bad bandwidth today. It says my signal is quite good, but hopefully I'll try to take it slow here and come back with questions, so we'll try to see it. That means that at an emergency stop, it's the external access that is stop, not the robot itself. Now we can control several external access on this part here. And it's also controllable through either a hardware interface, a wired interface, or a safety PLC interface. And likewise, we could then also indicate the status of this functionality back to a safety PLC in a group, for example. The next level of safety solution we have here is what we have named safe range monitoring. And safe range monitoring is, to describe it, a software axle limitation. That means, for example, for the robot 6-axis, we can limit them in how much they're able to move axle by axle. So you could say it's a virtual physical axle pins to block how much each axle is able to rotate. That means that we are controlling the axles one by one and not really the tool center point of the robot in this solution. However, this solution also comes with the functionality which is called braking before restricted areas, and I'll come back to that, what that is a little bit later on in this presentation. But as with safe single break, this can be controlled by a safety PLC or hardware interface, and will also signal its status back to a safety PLC, for example. The third and most complete product from our side is then the safe operation. And with safe operation, we can actually, for the one thing, define a virtual robot cell, which is significantly smaller than the reach of the robot, and the robot will not move outside of this box or limitation, thereby minimizing a footprint for a robot installation without actually hitting the fence, for example. The second part of this is that we can define up to 16 user-defined monitoring areas within this space, which can be turned on and off depending on external signals, which stops the robot from entering these areas. And we also have this functionality of braking before range limits. And in this solution, we can also define the size of the tool and the workpiece by defining a number of spheres that covers the tool itself. So it's not only the robot, but also the tool and the load, which is hindered from getting into these areas. And normally, of course, this can be handled through hardware inputs, but then it's a limited number. If we want the complete scope of zones, for example, we then have to use a safety PLC with a safety bus connected to it. And then it can be controlled by the PLC, but also reports its status back to the PLC this way. So here we can see the difference if we have put the robot into a cell and we are only using the axle monitoring, the safe range limitation, then only control the axle by axle, then we have to stop the axle from hitting the fence in this way. But with safe operation, we can move this fence in closer to the robot, still without risking that the robot hits the fence in this case, hereby freeing up valuable space in our production area. And this is also what we've described in this little picture here. We actually then defined a pretty tight, small working space allowed for the robots. In this little example picture, it's a very compressed working area allowed for this robot. But we could also then define monitoring areas or boxes within this space, which the robot is then not allowed to go into. And this could be used for different use cases. It could be the simple fact that there's a piece of machinery standing inside the cell, which I want the robot to not be hit during any circumstances. It also could be an area or a volume which is turned on and off, for example, through a light curtain. And that in turn is an area where an operator loads or unloads some equipment. And as I said, we could define up to 16 of these areas per robot, and they don't have to be, they can be turned or tilted in any direction as we like, and they could even be coupled to the robot base position if we have a 7th axle to the robot, so that these boxes would then move together with the robots as it moves along its 7th axle. In safe operation, we could also define spheres on our tool. I mentioned this earlier. That means basically that for each tool I have, I can define up to 12 of these spheres, which are meant to cover the volume taken up by the tool and the load. And these spheres are then taken into the calculation of the movement of the robot, so not even the load or the tool enters these restricted areas. And this picture basically just shows that one of the differences with our KSS 8.5 and onward is that we can now define 12 of these spheres per tool, compared to in the old versions 6 spheres, which gives us a higher resolution, so to speak, for the tool and the workpiece. So I'll let Andreas show you how this could look in terms of definition. So I'll just let the...
All right, can you see my screen now? Yes?
Yes.
Yeah, good. All right. There's 2 ways of configuring safe operation. Either you do it directly in Work Visual, or you can do it on the Smartpad itself. I usually prefer the Work Visual way to do that. It gives you a little bit easier interface. So first of all, the option has to be loaded in your project. It's here. And then under safety control, you have all the functionality. So by default, if you don't have the safe operation options, only the common tab is here. Now we have several more tabs. And the first one is the monitoring space. And you want to start by defining the cell area. It's defined by setting up positions, corner positions. You can have up to 10 corners, and you give them an X and a Y value in referencing the center of the robot. And then you put in a Z min, which is basically the floor. And then you have the Z max, which is the roof or the top. When you're done with that, that's your outer area. The robot will never go outside that area. And this is not, you can't turn it on and off. It's always there. Then we have spaces. And we've got a total of 16 configurable spaces. And you can give them names. Let's start by just, okay, now I can actually configure them. So you can give them a name, and you have to select what type of space it is. You have either Cartesian space, or you can have an extra specific space. So do you want to limit the area in a Cartesian way, or do you want to limit each and every axis? The safe operation allows the Cartesian space. The safe range monitoring only allows the axis specific space. So let's do the Cartesian. And is this a working space where you're allowed to work, or is it a protected space where you're not allowed to be? And then we have an activation. You can choose if it's always off or always on. That way, or by an input. And by input is usually a safety PLC or a hardwired connection, but it has to be a redundant, so it's a safe input. And if we want the robot to stop at the boundaries or not, usually we want to do that. And we need to do a mastering test, so to make sure that the tool and robot is where we think it is. You're using a 2-channel switch mounted somewhere in the cell, and then you have a fork-like object that you mount to your tool, and you use that, and you have to enable both of those inputs at the same time. That's the mastering test, and you can choose here if you need that as a prerequisite to enter the zone or not. So let's enable that for safety. And then we can restrict the velocity inside this protected space as well, if it's violated or if it's not violated. And then you set your speed limit by 1 millimeter per second. Next is to select your reference system. The world coordinate system is in the center of the robot. Rob root can be moved. Rob root reference the world coordinate system, but it can be moved somewhere else. For example, if you have a linear track. And if you want the space, the protected space, to follow the robot on a linear unit, you select the rob root, otherwise the world. And then you have to type in where you want the origin, the center point of your new coordinate system of your space. And then you basically drag it out in X, Y, and Z direction, and you get a box. So you got a total of 16 of these. Next is the axis monitoring. We can limit the velocity of rotational and translational axis. So rotational axis, usually the robot has rotational axes, and the translational would be a servo gripper or linear unit. And then we also have safety stops. Safety stop is when the robot is standing still, we can enable the safety stop monitoring from external input. And as long as that is high, the robot will monitor itself that it's actually standing still with drives on. And the benefit of this is that we'll be much quicker back to operation when the signal go low. We can start moving immediately. We don't have to, enable drives and so on. This tab is how we describe or how we model our tools. So first of all, you activate the tool you want to use. You can have several tools, and then you can switch between them from the safety PLC. And you give them a name and a TCP. The TCP here is not the TCP that you use in your program. This is the safety TCP. This is where we monitor the velocity of the robot. And then you can add your spheres. And every sphere has, you can select if they're supposed to be monitored or not. And then the X, Y, Z in relation to the flange of the robot. And then the radius of the sphere. All right. And then we have the braking before restricted area. We can enable that here. And this is working only for products with verified brake ramps. So our robots are, of course, verified. Our linear units are, but this is a servo gripper, not from KUKA, so it has an unverified brake ramp. And the last but not least is the reference position. Right now, the reference position, let's see, it's coming from an external interface. So we can have the reference position coming in from a PLC. The PLC says it's good, and we don't really care about it. If we have the reference switch supplied by KUKA, it's connected directly to the robot controller, and then we select the reference switch here, and this enables us to teach our position here. So there's two ways of doing that. You can either type in the position for the reference switch. I usually prefer to actually jog the robot to the position and teach it. And that's what you can do on the Smartpad. So I'm going to switch over to the Smartpad and show you the configuration interface here. It's under configuration and safety configuration. Easy. We basically have the same tabs down here that we have on the robot in Work Visual. I'm going to enable it and select the interface to reference switch. See here. So the big difference here is that you can actually jog the robot to the position and then press save. It saves the current position as long as these aren't red. And they are only red when you're close to the 0 position. So there's not much more to say about this. This is almost identical to what you can do in Work Visual. All right, let's see. We got a question. Are there any possibilities to define the safety zone and tool coordinates by CAD data? Typically, it's very difficult to give a clear overview of the defined spheres and zone by only the Cartesian coordinates. I would say you can use the CAD data as a base, but you still have to type in the numbers in our configuration tool. Do we have any other questions? All right, I'll leave you back to Michael again. Let's see.
So the last slide regarding our product is this table where we see the difference between the three different software products. And as we see here, for safe operation, basically handles all the options which are covered by the lesser products. For example, 16 safe tools with safe TCPs, which Andreas mentioned here. We can monitor the velocities of the axles within the confined spaces and limit them if we like as well. Now, we talked a little bit about braking before restricted areas and a few words of what that is. If we need to stop the robot during a movement or along a path which then follows this curve here, if we just hit the mechanic brakes, the robot will obviously continue a little bit along its movement direction, and the end up where we come to a complete stop is a little bit unknown. So what braking before restricted areas actually do is that it knows where the robot is currently, and it knows the planned path and velocity, so it can predict where it will end up within the next few time frames. By using this, it can actually, if it comes very close to a fence or a restricted area, for example, actually limit the speed a little bit. So it's at each time has the possibility to stop the movement before it enters the restricted area. Now we can do this as this example does, that we just stop the robot, but we are still leaving the path, but we are not entering the restricted area. But we could also define this as a path stop. That means that we still have the same path. We could end up inside in a restricted area, but using this functional, it will limit the speed, and at a safe stop one, could decelerate and to a complete stop along its path. That means that we have a much shorter time of restarting ourselves again because the robot is still on its movement path. So that is a functionality that's found within safe operation and safe range monitoring. And finally, if the load is so heavy or the speed is so high, so it's really impossible to keep it on its path, it will try to stop the movement to ensure that it's always stopped before it enters the restricted area. Any questions on this? Because that pretty much concludes what me and Andreas wanted to show you a little bit about today.